Hello, everyone. Welcome to another seminar. Today, our guest speaker is Silvia Goncalves, and her guest panelists are Lutz Lütkepohl, Ana Maria Herrera, Lutz, Kilian, and Elena Pesavento. The talk will be for 1 hour and will be recorded. If you have questions, please feel free to unmute yourself and ask the question. Silvia, the floor is yours.
Thank you. Thanks a lot for being here. So today I'm going to present some recent work with this set of co-authors. And let me just, why is this moving? Okay. Let me just start by introducing the subject. So of course, we all know that impulse response functions play a big role in macroeconomics. And here we're interested in impulse response functions that allow for state dependence. And by that, I mean the possibility that impulse response functions may differ depending on whether the economy is in a recession or in an expansion. This has been studied in the macro literature by a number of authors. Here I'm just citing 2 strands of this literature that has allowed for state dependence impulse response functions, starting with the government spending or fiscal shocks literature, where there was an interest in providing impulse response functions that allowed for regimes of expansions and recessions. But this is not limited to this literature. If you look at the effect of monetary shocks in macro outcomes, you again see papers having been written that allow for state dependence. And I could have included other types of shocks here, but the bottom line is that people care about impulse response function analysis, and increasingly they care about the possibility that these impulse response functions are state dependent. Now, the usual way that one would do allow for state dependence would be to construct impulse response functions from structural VAR models that allow for state dependence. But increasingly, people have looked at this alternative way of computing impulse response functions, which is via local projections. So these have become very popular in this literature. They've been popularized by Jordan in 2005. And the reason why these are very popular is that, of course, the idea is that we run a set of OLS regressions, one for each horizon of interest. And so we don't have to estimate the whole structural model underlying our data. So they're very easy to compute. And that's particularly the case in nonlinear models, such as the one that I'm going to describe later, because say you wanted to obtain an impulse response function for GDP growth to a shock in government spending, and you want it to depend on being in recession or an expansion. What you do using the local projection approach is to regress GDP growth, for instance, on this measure of the shock, interacted with the dummy variable that tells you whether you're in an expansion or in a recession. This can be estimated by an OLS regression. So again, it's very easy to do. And if you contrast that with the alternative approach of obtaining impulse response functions via a structural VAR model that allows for regime switching, this is much, much easier. And so they're really popular, especially in the context that we're talking about here today. Now, despite the popularity, we couldn't find any work that has established the validity of these nonlinear state-dependent impulse response functions within a nonlinear model. And that's what we are set to do here. So the main goal of this paper is going to be to provide a set of conditions that will allow us to prove the consistency of the state-dependent impulse response function that you get via a state-dependent LP. Now, let me just introduce some notation. Here I'm going to take, again, one of these main examples in the government spending literature. And so suppose that you care about the impact of a government spending shock, which is going to be epsilon 1t here, on output growth. And you want to trace this effect over time. So H is the horizon of interest. What you do using a state-dependent LP is you run a regression for each H, where you project YT plus H onto this measure of the government spending shock, which you could identify through a narrative approach, for instance, interacted with a variable that I'm going to be calling HT minus 1. And this variable will be a state indicator. So it will tell us whether we are in an expansion or in a recession prior to the shock. Typically, this regression would include some additional control variables that will be in this vector WT minus 1. But the main parameters of interest are going to be the ones in red here, because they will tell us the impulse response function for periods of expansion and recession. Now, for the story that we're going to tell today, the variable H will play a crucial role. So as I said, this is a dummy variable that takes the value 1, for instance, if we are in an expansion, and 0 otherwise. And what's important to note here is that this variable H is actually observed. It is constructed by the researcher using some information available. And so depending on the study, we have different information sets used to construct this state indicator. So here I'm citing 3 studies. In the first one, one example that was considered was to date recessions if the unemployment rate is above 6.5%, I think. In other studies, different data was used to construct H. So for instance, in our Var and Goronichenko, H was based on a 2-sided moving average of GDP. In this other paper by Alhoza, H was also based on GDP, which is the outcome variable in this equation here. So the bottom line here is that different researchers use different variables to construct H. H is observed, and so we can easily, once we have these state indicators, we can easily obtain the parameters in red, and these parameters denote the impulse response function in expansions, because when H is equal to 1, that's the coefficient in front of epsilon 1, or in recessions would be this guy here, because when H is equal to 1, 0, we're in a recession, and so these would be the coefficient that would prevail. And so, as you can see, this is very easy to do once we have this variable H, and as I said, the main goal of this paper is to try to justify theoretically this approach by coming up with a set of conditions under which this approach would deliver some meaningful notion of impulse response function. And so this is my one-side description of what you think are the main contributions of our paper. As I said, the main idea is to study the consistency of this state-dependent LP. And the way we're going to proceed is by writing a class of state-dependent structural VAR models that allow for state dependence through this variable H that I just introduced. And then we're going to use this DGP to evaluate the limit in probability of the state-dependent LP estimator, which is just an OLS coefficient, as you could see in the previous slide. What we find is that if the state indicators, these variables H, are exogenous with respect to the shocks in the model, in the sense that they're not correlated with epsilons in a given precise sense that I'll tell you later, then this approach works in the sense that these coefficients in red will identify a notion of conditional impulse response function that I'll present to you later, which is meaningful. And so when this approach works, the LP is actually much easier than the structural model-based impulse response function, which you'd get from a structural VAR, in particular from the one that we write in this paper. And in the sense, why is it easier? Again, because if you were to use the structural VAR model to generate impulse response functions, you would typically require simulations. And so that's more complicated than just running an OLS regression. We would argue that when it works, LP is also more general than a structural based VAR approach, because As you could see from the previous slide, we don't actually need to specify a data generating process underlying the process, the variable HT, the state indicators. So these transition probabilities can be very general. They don't need to be specified. And that would not be the case if you were to simulate the impulse response functions, because you'd have to have a way of simulating future states. So in that sense, this LP approach, when it works, is easier and it is more general than what we think would be the alternative way of computing conditional impulse response functions. Now, the problem is that...
Silvia,
yes?
just one quick question. So,
sure.
So here you is like considering two states, like 0 and 1.
Mm-hmm. Mm-hmm.
So what if you, in case if you consider many states, so is this second point still valid?
Okay, so that's a good question. So we for simplicity, and also because many people in this literature limit themselves to these two states, we've assumed indeed two regimes.
Right.
But there are some papers that allow for a smooth transition. If you look at the Auerbach and Gorodnichenko's papers, they do allow for a class of structural models where the transition is continuous as a function of some information variable. But then at the end of the day, they still plot two impulse response functions, one for expansions and another for recessions. So the answer to your question is that we haven't investigated what happens when you allow for a smooth transition rather than these two regimes. And so I can't really comment on what would be the case, whether we would, so you're wondering whether we would still be able to capture LP, the impulse response function through an LP approach. Again, the LP approach typically is based on this H variable. And so you don't require really the DGP for H, I don't think.
Okay, and so I'm not sure what you do later, but regarding this paper, so the analysis is done conditional to the state, right? I mean, not is it conditional or unconditional? So
conditional.
Like, conditional.
Conditional, but actually that will become much clearer later.
Okay.
We're actually after the impulse response function that conditions only on the value of the state indicator H prior to the shock. So we have to integrate out a number of randomness that comes from the future states in particular. And so why do we do that? Why do we care about this impulse response function? Again, because that's what we see macroeconomists reporting. They report impulse response functions for expansions and for recessions. Other notions of impulse response functions could be entertained. You could maybe condition on being always in an expansion from now on.
Yeah, I mean, I thought about like going unconditional. It's like I have no information whether we are in this recession or expansion, and then build a sort of like unconditional, impulse response function where the econometrician doesn't know which state we are, and then. So that's what I thought.
Yes. And conditional impulse response function could be also computed. We actually have a different paper that came out in the Journal of Econometrics last year where we considered unconditional impulse response functions within a different model, but we could certainly approach the problem within this particular model that I'll show you.
Okay, many thanks. Thank you.
Now, as I was saying.
So Silvia, very, very quick one. Sure. You might have said it, I might have missed it. Is the exogeneity with respect to all shocks driving Y or to the shocks that are of interest for us? So
he says, the assumptions that I'll give you will be with respect to the all shocks in the model.
All shocks. Thank you.
Now, as you'll see later on, what happens when these state indicators are endogenous in the sense of being correlated with the shocks in the model is that although we couldn't, analytically characterize the asymptotic bias in this state-dependent LP estimator, we actually show via numeric evaluation for different models that there can be a bias. Okay, and so our assumptions that I'll show you later, which justify the LP approach, certainly are violated when the state indicators are endogenous. And we have evidence based on these simulations that indicates the presence of a bias. And so that's the bad news for the state-dependent LP. That doesn't mean that, for all models, you'll have a bias, but you could have a bias. And the main reason that this approach, fails to recover our notion of impulse response function when the states are endogenous is that it actually does not account for the possibility that when you perturb a variable today, so when you introduce a shock today, these could change the trajectory of future states. And so essentially, which could be the case if the states are endogenous. And so that's not accounted for in the state-dependent LP. And this is one of the reasons why the approach may fail to work in this case. So that's the one slide contribution. Now let me just describe what we're going to do in the rest of this talk. So I'm going to describe very briefly the set of models that we have in mind. This is going to be a multivariate state-dependent Var model. And then I'm going to propose a notion of the conditional impulse response function that allows for state dependence. And very quickly, I'm going to turn to a bivariate model to illustrate this conditional impulse response function definition. And many of the results that I'll describe in the presentation will be for this simple bivariate model, where epsilon1, the shock of interest, is identified via a narrative restriction. Then I'll describe the consistency result we have and the assumptions that justify the result. And then at the end, I'll discuss briefly what happens if these assumptions are not verified when state indicators are endogenous. And I'll show you that those simulations that illustrate the possibility of a bias, and then conclude. So here's the data generating process we have in mind. So this is a standard structural VAR model with state dependence. So think about ZT as a vector, a k/1 vector, where the first variable xt is the variable that we're going to shock. And yt is a vector that contains one or more macro variables of interest. And our goal is to quantify the effect of shocks in xt on the variables in the vector y over time, okay? Now, the model here is the structural Var model. So the epsilons here, which will be decomposed this way, will contain the structural shocks to each equation. Epsilon1, as I said, is the main shock of interest here. So if X was government spending, epsilon1 could be the shock to government spending. And then YT could contain output, tax revenues or other variables, and those would be the variables, the outcome variables of interest. Now, the equation here has the matrices C, mu, and B indexed by t-1, and this is because we're going to allow for state dependence, and the way we're going to allow for that is by introducing this variable h that I showed you before, which takes the value 1 if we are in expansion at time t-1 and 0 if we are in a recession. And so we're allowing for the parameters in these matrices here to change between these two regimes depending on whether we were in a recession or in an expansion prior to the shock in epsilon1t. The goal will be to recover the response of yt plus h to this one-time shock in epsilon1. And again, the focus will be to obtain this response conditionally on being either in an expansion or in a recession prior to the shock. So that's the object of interest. Now, if I don't impose further restrictions on this model, then I won't be able to identify this impulse response function. That'll be already the case in a time invariant VAR model, as we all know. And so here's the identification conditions that we're using in the paper to identify this conditional impulse response function. And essentially, the key identification condition is that we assume xt to be predetermined with respect to yt. So I'm excluding the possibility that xt reacts contemporaneously to the variables in the vector yt. So that means that we're allowing for the shock epsilon1t to be identified via short-run restrictions within this model, or a special case, which is quite important in this literature, is when we think about xt to be epsilon 1t in the sense of, being the shock itself. That would amount to a narrative identification approach where you look up exogenous information to measure the exogenous shock. That has been done in the government spending literature by these authors, and it's quite popular, as we all know. So this is our key identification condition. And I would like to note too that the remaining part of this model, when k is larger than 1, so when we have more than one variable in yt, we're actually not going to restrict any further the coefficients in this block of equations here. And so in that sense, this model is only block recursive, which means that the shocks epsilon 2t may not be identified when we have a trivariate or larger dimensional VAR model. That's not an issue for us because our goal is to identify the response of the variables in the y vector to shocks in epsilon 1, and epsilon 1 is identified within this model. The next point is, how should we define a conditional impulse response function? There's many notions of conditional impulse response functions, or in general impulse response functions, as we've discussed already before. And this is particularly the case in nonlinear data generating processes, such as the one that I'm talking about here. So what we do is to draw on this older literature that has discussed extensively nonlinear impulse response functions. And the main idea is very easy. So we want to trace the effect of a perturbation in epsilon 1t, let's say government spending shock, on variables yt over time. And so what we're going to do is we're going to consider two sample paths for these variables y. One that is associated with a baseline sample path where no perturbation in epsilon 1t is considered, versus another sample path for y where we perturb epsilon 1 by adding some shock, some perturbation delta. So I'm going to refer to this sample path as a counterfactual. And so essentially what we're going to do is we use this model as a lab and imagine that we perturb epsilon 1 at time t by adding delta to it. With all the other shocks are the same between the counterfactual and the baseline. And then we compare these two sample paths to come up with a definition of what would be the effect of this perturbation in epsilon 1 on the outcome variables, everything else being the same. So that's the main idea. That's not an idea that is novel to our work. As I said, we draw on this nonlinear impulse response function literature, and this, there's a vast number of papers written on generalized impulse response functions. So our concept is quite related to what you would see in that literature. Now, more formally here is a slide that describes this baseline versus sample counterfactual sample path for y. And so let me just spend a little time on this. So imagine that I give you a sequence of shocks, epsilon 1s and epsilon 2s. Those are the structural shocks in the model. And I also give you a sequence of state indicators. In the model that I presented so far, I didn't tell you how these H variables are generated. So those can be thought, if you would think about it generally this way, as primitives. So if I give you this sequence of epsilons and h's, you can feed them into the model and obtain a sample path for y. I'm going to denote that by y, and that will be the baseline sample path. Now, suppose that you now consider an alternative sequence of shocks and h's, which I will call the counterfactual shocks and state indicators, where the only difference with respect to the baseline shocks and state indicators is the following. For the structural shocks, all the shocks except epsilon 1 will be the same. So in the counterfactual, I perturb epsilon 1 by adding delta to it. And I'm going to call that epsilon 1 star. Everything else is the same. And now, because this epsilon 1 shock may change the state indicators contemporaneously and in the future, I'm also going to allow for the sample path of state indicators to be different between these two sample paths from time t onwards. And so that's why you see in red here, h star t plus 1, etc. Okay, so this is to accommodate for the possibility that when I perturb epsilon 1t, if ht is a function of epsilon 1t, that could change the state indicators. Now, given these counterfactual shocks in state indicators, I can again solve my model and obtain values for y. I'm going to call those y stars. And these are the counterfactual values of these target variables implied by the sequence of counterfactual shocks and state indicators. So now we have a counterfactual and a baseline value for y, and we can take the difference between these two. In general, because this model is nonlinear, this difference will be random. And so what we are interested here in is computing the conditional expectation of this difference, where we condition on the value of h prior to the shock. That's going to be our definition of conditional impulse response function. Okay, so we are interested in quantifying the effect of a one-time shock in epsilon 1 on the variables y, conditioning on being in an expansion or in a recession prior to the shock. You could stop me and say, why would be this? Why is this the only definition? Well, we've already discussed with Abderrahim before that there could be other notions of impulse response functions one could entertain. So for instance, I could simply take the unconditional expectation. That's something one could care about. The reason why we focus on this particular one is that, again, what we are trying to justify is the empirical practice where we see people computing impulse response functions for expansions and recessions. And so that's why we focus on this particular notion. But again, let's be clear, there could be different notions of conditional impulse response functions we could care about.
Maybe just one question regarding the set of shocks that you are using. Would it make a difference in your model setup if you take all future shocks to be zeros? Would that change, this difference between yt star?
If all these shocks would be zero, you'd have less randomness, and it would change the way you evaluate this definition.
So it could make a difference.
Yes, it could make a difference, in fact. But, and I think, in fact, in the nonlinear impulse response function analysis that people, that I cited before, that was actually one way to deal with the nonlinearities, just set all these future shocks to zero.
Yeah, but that is definitely, it's not the same in all nonlinear models, what kind of sequences of epsilons you are considering. And therefore, I was asking whether your model may be slightly more limited in that respect, but it does seem to capture that as well.
No. I think that the definition in general, certainly if you were to fix the epsilons in the future being zero, that you have a different impulse response function. How does that impact the state dependent LP? That I don't know, because our view was that, well, we're really trying to see, if you were to perturb only epsilon 1 and nothing else, but not assuming that there's no randomness in the future. No, we want to allow for randomness. And so in fact, we have to integrate it out. Okay, so let me go on. And so what I want to do next is to kind of go through this definition in the context of a very simple model that we will all follow. And that's going to be a bivariate model where x is equal to epsilon 1. So I'm going to be thinking about a narrative identification approach. Let's say that I've observed a measure of disgorgement spanning shock, as in Ramey's work, and that's my xt. And then I'm also going to simplify a lot the dynamics in the equation for y by only allowing one lag of y and the contemporaneous values of x here. as before, I'm going to induce state dependence by allowing this parameter beta and gamma to change depending on the value of h. And one example could be if we think about h as being this dummy variable that depends on unemployment. And so I'm going to say, if unemployment is sufficiently low, this is an expansion. Okay, that, as I said, was done in some of the literature, in the government spending literature papers. So what I'm going to do next is evaluate the definition I proposed to you for the conditional impulse response function, setting h star equal to h. So I'm going to be thinking about a counterfactual where when I introduce a shock in epsilon 1t, on impact and in the future, the values of these state indicators will be the same in the baseline version of the model versus the counterfactual. And that would be completely consistent with the idea of treating the information set used to construct this dummy variable as being exogenous with respect to epsilon. Okay. So what do we get then? Well, if you recall that this is a model where x is equal to epsilon 1, and I'm thinking about one perturbation of size 1 in epsilon 1, I can use the model equations to obtain the baseline value for y, which is the version of the model without the shock, versus the counterfactual value of y, which we called y star, which is the version of y when you introduce this shock of size 1. And so using the model equations, you see that the only thing that changes in between them is what's in red. Everything else is the same. And that has to do with the fact that I've told you all the other shocks remain the same. And I also told you that, well, the timing here is very important. The equation at time t depends on ht minus 1, right? This beta t minus 1, this index here means that in the model we're talking about, the parameters are dated using information at time t minus 1. Well, since we've assumed that nothing has changed between the baseline and the counterfactual up to time t, these parameters are the same in the two equations. And so when you take the difference between y star t and yt, you get easily beta t minus 1. Okay. Now this beta t minus 1 being a function of ht minus 1 is a random variable. And so that's where we need to somehow integrate out this randomness, and our proposition, our definition is to take the conditional expectation conditioning on this variable being 1 or 0. Okay. And so, of course, you can immediately see that if we're thinking about expressions at time t minus 1, then beta is beta e, beta t minus 1 is beta e, and otherwise it's beta r. And so now we have on impact an impulse response function that has these two different values depending on expansion or being on a recession. So that's easy. Now, what happens for h equal to 1? When you use the model equations to evaluate y and y star t plus 1, of course, now at time t plus 1, t enters the equation. And so we see that in the counterfactual version of the model, y star t is not the same as yt, so they're in red here. And then the other thing is that the parameters that drive the evolution of yt plus 1 are now dated t. And these are a function of ht. Since I, perturb epsilon 1 at time t, it could be that these parameters change in the counterfactual if ht reacts to epsilon 1. However, I told you to consider a setting where h star is equal to h, right? I shut down that channel. And that's why the parameters in the equation for y star, these guys here, don't have a star, because my choice of counterfactual, which treats the future states as being equal across these two versions of the model, allow me to say that these have to be the same. And so with this in mind, you can now see that when you take again the difference between the counterfactual and the baseline value at time t plus 1, what you get is gamma t times this difference, but this is beta t minus 1 as we saw before. And so again, we get now a random variable, and our definition says take the conditional expectation of this random variable, conditioning only on ht minus 1. And so you can easily see what that gives us here, because if I condition on being in an expansion at time t minus 1, then beta t minus 1 is beta e, so it can come out of the expectation. However, conditioning on being an expansion at time t minus 1 doesn't mean that we are still in an expansion at time t, right? So this gamma t being driven by ht is random, conditionally on ht minus 1. And so we take the conditional expectation. And same goes for periods of recession. We start with the recession. It could be that the economy at time t is either in a recession or an expansion. Applying the conditional expectation operator gives us this expression. So it's important, you can immediately see that this generalizes for larger values of h, and in a very natural way, which is that, again, thinking about counterfactuals where h stars are equal to h's, we get an expression for the conditional impulse response function that now has this form here. And again, notice that because we're only conditioning on ht minus 1 being 1 or 0, we're not conditioning on future states or not even path states, right? What we do is we integrate out these randomness by taking these conditional expectations. So that's quite important to notice, because when we read some of these papers that use the state-dependent LPs, it's clear that sometimes people may assume that you start in an expansion and you stay in an expansion. It's important to see that we're not allowing, we're not restricting ourselves to that. We're actually not conditioning on future or current states of the economy. Now, we got for this very simple model an expression for the conditional impulse response functions, and one could ask, can we use those to come up with impulse response function estimators? And yes, we could, but this is actually analytically challenging, because you could see from the previous slide that we still have these conditional expectations. So clearly, if I had a model for HT, I could try to evaluate these expectations. Analytically, that's hard to do, but what people tend to do in this literature is simply to use Monte Carlo integration methods to approximate those expectations. So that, I would say, is the standard practice if you don't want to use an LP approach. Of course, local projections are much easier, because you don't have to use simulations to approximate those expectations. You just run OLS regressions. And again, remember that we don't need to actually model how HT evolves over time. That would be typically required if you were to follow these alternative approaches. So the goal, again, of the paper is to try to justify the state-dependent local projections. And so I'm going to next describe a set of conditions that will allow us to claim that the OLS estimators that I defined at the beginning will converge in probability to the conditional impulse response function that we just got. Okay, so that's the goal in the next few minutes. Now, the first assumption is a very standard assumption in this literature. It just says that the vector of structural shocks conditioning on the path have mean 0 and the covariance matrix sigma. So essentially, I'm imposing a Martingale difference sequence assumption on the epsilons. This matrix sigma here is a diagonal matrix. I don't think that's very controversial. These are structural shocks, so they should be mutually uncorrelated. What could be more controversial, I suppose, is the fact that we're assuming these variances to not be time varying. So we're ruling out conditional heteroscedasticity. It turns out that this actually has a bite in terms of the proof of the results. So I'm going to argue next that this assumption alone is sufficient to show that the LP estimator is consistent on impact when H is equal to 0. So how do we show that? Well, first thing is recall what this OLS estimator is, right? What is the state-dependent LP? It's just a OLS coefficient. And for simplicity, let us focus on the case where we care about expansions only. So if I cared only about the impulse response function on expansion, the first thing to notice is that, well, I would run this regression, But here you see, this is where the fact that H is a binary variable helps a lot. First thing to notice is that if I cared only about this coefficient here, since H and 1 minus H are exactly orthogonal, I can drop anything that depends on 1 minus H, right? So I just run a regression of YT plus H onto these X interacted with H and controls interacted with H. I only care about these guy here. I don't care about these. These are controls. And so I can use the Frisch-Wallow theorem to obtain an expression for this coefficient and get its limit. And that's what I show you here in the next page. So easily using FWL theorem, you get that the limit is this expression here. And, you know, it looks complicated, but it's actually very easy. And in particular, it's very, very easy when X is equal to epsilon 1, which is the model assumption I've been asking you to entertain for the bivariate simple model. And that's because if X is equal to epsilon 1 would show up here. And these guys depend on information at time t minus 1. So by the law of iterated expectations, these expectations are 0. So they drop out. And so what you get is that in the limit, when you recover this OLS coefficient, it's going to behave like this. It's this simple ratio here. And because H is binary, you can actually write this ratio of unconditional expectations of a ratio of conditional expectations. Okay. And this helps a lot with the interpretation, because what this formula is saying here is that in the limit, my state-dependent LP for an expansion behaves as if I projected the outcome variable on xt, conditioning on being an expansion. That's what this formula is telling us. Now you could, you know, this interpretation actually will follow even when X is not a narrative identified shock, you know, then you'd have epsilon 1 here and epsilon 1 here. So it's again, this very simple ratio of conditional expectations. So the next question is, can I show that this ratio of conditional expectations is anything like the conditional impulse response function that we derived? And the answer is that yes, when H is equal to 0. And for that, I don't actually need to, you know, put any restrictions on how H depends on the shocks. And so what we show in the paper is that under assumption 1 alone, plus assuming that the data is stationary and ergodic, which I'm assuming throughout to be able to obtain these limits, this coefficient here will be just, again, is the result of projecting YT onto X, conditioning on being in an expansion, and we can easily show that that's beta E. But beta E is exactly what we found out to be the conditional impulse response function on impact when we are in an expansion. Okay, and so the point I would like to emphasize here is that to get this result, and I'll show you heuristically why it holds, we actually only need the martingale difference assumption on epsilon. We don't need to restrict how H and epsilon are statistically related. And so that means that on impact, even when HT is endogenous, we can recover the impulse response function conditioning on being in an expansion on impact. And of course, the same result would hold for the recession. So how does this work? Well, remember that I've emphasized the fact that when we're doing this LP estimator, essentially in the limit, we're projecting YT plus H on XT, conditioning on being in an expansion. So when H is equal to 0, essentially what we're doing is projecting YT onto XT, right? And immediately you see, using the model equations, that if I told you that we were in an expansion at time t minus 1, the beta t minus 1 would be beta E and gamma t minus 1 would be gamma E. Okay, and so the question really ends up being the following. Can I show that the error term in this underlying regression is orthogonal to X, conditioning on being in an expansion? If so, then of course projecting or regressing YT onto X alone will give me beta E, but beta E is exactly the impulse response function on impact. And so then I'm done. And so the question is that it's very easy to see that's going to hold under assumption 1. Because if you know the error contains YT minus 1 and epsilon 2, if you look at these two conditional moment equations, well, you see that by using, well, first of all, remember X is epsilon 1, And so if you, and here I'm only conditioning on being in an expansion at time t-1. But I can use the law of iterated expectations to condition on the whole information set up to time t-1. And then what I get is these iterated expectations here. And the bottom line is that the terms in red drop out, they're 0 under the martingale difference sequence assumption. And so that's why we can conclude that the state-dependent LP on impact will recover beta E when we condition on being in an expansion. And that doesn't require any other assumption besides assumption 1. Now, I'll show you next, or I'll argue next, that this is no longer true when you move beyond H equal to 1. So for larger values of H, you need further restrictions to conclude that the state-dependent LP gets something close or equal to what we derived as being the conditional impulse response function. And so how do we get that? And that will give rise to the assumptions that we give in the paper. Well, remember, so focus on H equal to 1, since these will give us the main ideas. Remember that then what we're doing is projecting yt plus 1 onto xt interacted with ht-1 and a bunch of controls. But really in the limit, this projection will actually identify this ratio as I showed before. So this is, again, the very simple ratio, which, because H is binary, can be written as this ratio of conditional expectations. And so it's, again, nice to think about this as saying that in the limit, this guy here will behave as if I do a simple OLS regression of yt plus 1 onto xt, conditioning on being in an expansion at time t-1. And so why is the problem more complicated now? Well, the problem, again, has to do with the fact that I'm only conditioning on what happens at time t-1 in terms of the state indicator. And so if I tell you that ht-1 is 1, the equation I get for yt plus 1, which is the dependent variable in this OLS regression, is still state dependent. And this is easily seen because, you know, the equation for yt plus 1 depends on beta t and gamma t. And those guys depend on ht. And so now let us think about a simple OLS regression of yt plus 1 onto xt. So you can rearrange this equation so that the only regressor is xt, and put everything else into vt plus 1. Well, now vt plus 1, the error term underlying this OLS regression, is going to contain terms that depend on gamma t and beta t. So this vt plus 1 will contain ht. And so you can heuristically see that to get you know, something that relates to this term here, when you're projecting yt plus 1 onto xt, you actually have to restrict how xt relates to ht. And so that's what we do in the paper. We show that under an assumption that I'll show you next, if xt and ht are appropriately uncorrelated, then what you end up obtaining when you project yt plus 1 onto xt is the conditional expectation of this term, conditioning on ht-1 equal to 1. But that's exactly what we found as the conditional impulse response function for h equal to 1. Okay, so that's the main idea here. And the assumption that allows us to conclude this result is this assumption X. So it's just a sufficient condition. There could be other ways of you know, getting the same result. But we thought that this assumption is quite natural, because what it says is that conditioning on the past, we're you know, excluding the possibility that the first and second order moments of the shocks in the model depend on ht. That's what this assumption is saying. So it's a conditional moment independence condition, and it's quite natural that it takes this form because OLS, we're doing OLS, right? And OLS depends on first and second order moments of epsilons, and that's what this assumption is allowing us to recover. It's allowing us to show that the LP estimator recovers that conditional impulse response function. And so we're restricting the dependence of epsilon and h at time t, conditioning on the past. Now, when would this assumption be satisfied? Well, one obvious case if the process underlying h is completely independent of the epsilons. So that's a form of strict exogeneity under which assumption 2 is satisfied. So for instance, I told you before that, sometimes people have used unemployment to date recessions and expansions when looking at the effect of a government spending shock on output. So if we were to assume that unemployment was completely independent of the shocks in this model, the shocks to government spending and output, then this assumption would be satisfied and the LP estimator would be consistent. Of course, this is a very restrictive assumption. Now, the advantage of writing assumption 2, rather than just telling you, let's assume H to be completely independent of epsilon, is that, well, one way to make it work is to date recessions and expansion at time t using variables in this set, right? So if I was to use an output to date recessions and expansions using information dated t-1 or before, then HT would be already in this information set, and these would be automatically satisfied. So that's the advantage of writing it this way. One case where this is not satisfied or may not be satisfied is if HT depends on YT. And the reason is that if HT depends on YT depends on epsilon t. If you think, for instance, about part A here, one of the conditions or one of the requirements would be that the conditional expectation here has to be equal to this conditional expectation. So including HT doesn't change the expectation. However, if of course HT depends on YT this way, epsilon 1 and giving you this restriction amounts to truncation. So this would be a truncated moment for epsilon 1t, which is not the same as the untruncated one. And so this is why this assumption would not be satisfied if you use the outcome variable to date recession. Okay. Now, of course, assumption 2 is only a sufficient assumption. It may not be necessary. So it could be that even in this case, you get no bias or a very small bias. That will have to be evaluated on a case-by-case scenario, I think. Now, let me skip the proof. Let me go on to what one would expect when looking at larger values of H. So clearly, you can see that if you consider larger values of H, then you again have this result where you're projecting YT plus H onto XT, so simple OLS regression. And now what I had called VT plus 1 is VT plus H. And clearly, that error term will contain all the paths of the H's up to time t plus H minus 1. So it's very natural that to get the same sort of result as we got for H equal to 1, we now have to include all the future values of H up to this date. And so again, the general formulation of assumption 2 would require a moment independence condition where we're now restricting dependence between the epsilon and in terms of its first and second order moments and this path of the H's, conditioning on the path. So if, again, assume strict exogeneity, this is clearly satisfied. But if we think about another less stringent way of satisfying assumption 2 in this general case, for instance, think about H equal to 2. What this condition is saying is that the first and second order moment of epsilon t should not depend on HT and HT plus 1, given information at time t minus 1. So one way you could have this assumption verified is if you use information on Y to construct HT, but you only use second or third order lag. So any information up to time t minus 2 would work in this case because clearly this guy is in this information set. And when you go and look at what happens at t plus 1, now you'd have t minus 1 and t minus 2, and these would be still in this information set. So that would be another way to have this assumption 2 verified. So of course, you could say immediately, I mean, yeah,
just remind
nice.
You've got some 5, 6, 7 minutes.
Yeah, that'll be fine. So I just wanted to say, of course, I gave you an example where you don't have to assume strict independence between epsilon and H for these assumptions to be satisfied, but it's pretty clear that as you increase H, you'd be using, if you follow this route, you'd be using farther and farther away information on Y to date recessions and expansions. So eventually, you know, if you consider the whole impulse response function, you need to assume some sort of independence. So that's one way of reading his assumption. Now, I want to end the talk by thinking about this more interesting case where HT is driven by YT. And so for simplicity, let me assume that it's just given by this function of Y. The first implication is that we can't anymore set H star equal to H. That was, you know, we used this condition to derive that nice expression for the conditional impulse response function, but this is no longer going to be applicable if H is a function of YT. And the reason is that essentially, I'll show you next, that when you perturb epsilon1 at time t, YT changes. And so that means that in the future, YT plus 1 changes. And so H in the future will change with respect to what you had in the baseline model. And so what you end up showing is that when you take the counterfactual value of Y and compare it with the baseline, you're going to have two terms. One, which is what we got before when we fixed H star equal to H, and we're going to call that the direct effect. And then you're going to have extra terms, which we're going to call the indirect effect. And these extra terms will capture the fact that when you perturb epsilon1 at time t, if H is endogenous, that could affect the values of H in the future. And therefore, this H star won't be the same as H. And so, you know, quickly look at what happens here with the bivariate model we worked with so far. So on impact, because of the timing of the model, we still get beta t minus 1 for the difference, since we've assumed that up to time t minus 1, everything was the same between Y and Y star, the two baseline and counterfactual sample paths. But at t plus 1, so for H equal to 1, the difference between these two will have what we had before, which was this term here, plus these extra terms. These extra terms, if you remember, had some, you know, I emphasized the fact that they were in blue before, that we set beta star t equal to beta t, because we set H star t equal to HT. But now that's not the case anymore, because if you look at the formula for gamma star, for instance, it's given by this, but this H star cannot no longer be assumed to be equal to H, because H star is driven by Y star, but Y star is not the same as Y. And so that is why when you have this sort of endogeneity, these parameters could change. Okay, and so that shows up as extra terms when you take the conditional expectation. And those extra terms are what we call the indirect effect. Of course, as you move further ahead, you get more and more extra terms. So these are the indirect effects that you'd get. So that's one difference. The other one is that if we want to evaluate this limit, it seems is a very simple ratio of conditional expectations, but without assumption 2, actually analytically evaluating these is very challenging, even when you assume Gaussianity, for instance. And so what we do is numerically evaluate the asymptotic bias by evaluating these numerically and contrasting it with the conditional impulse response function. And so that's what I'll show at the end. I have some simulations here for different DGPs. It's a bivariate simple model where X is either AR1 or X is equal to epsilon1, which is the narrative approach to identification. And then we're going to allow for one leg of X and Y in the DGP for Y, and X is also showing up. And so the first DGP is the exogenous H. So I generate some QT that is exogenous. And that's just to show you that, of course, we get what we would expect. Everything works. And then we have a set of DGPs where we endogenize H by letting it be driven by this model. And then the DGPs differ depending on the parameter values. And so I'm going to show you, to end the presentation, two types of objects. The conditional impulse response function in levels that we've been talking about, but I'm also going to show you a cumulative version, because that's what people tend to care about when they're looking at multipliers. So you sum them up to H horizons. And then we're going to contrast those population objects of interest with the estimates you'd get from LP, both in level, which is the OLS coefficients we looked at, and their sum, which would be like the analog of the cumulative conditional impulse response function. And everything will be evaluated through simulations, because again, when H is endogenous, it becomes intractable to actually obtain a solution for this. And so here's the DGP1. This is just a very simple model. I have 4 kinds of points here. In blue, this is the population conditional impulse response function at different horizons. In red, I have the LP estimate, and you see it sits in top of the blue line, saying that it works. And then we have the direct and the indirect effect. And of course, in this model where QT is generated exogenously, HT is exogenous, so the direct effect is the conditional impulse response function, and the indirect effect is 0. Okay, so this is not very interesting DGP. This would be the cumulative version. Let me now show you what happens if I endogenize HT. So now, still in blue, we have the population impulse response function we would like to recover. In red, we have the LP estimate. And then we have this dotted line, which is the indirect effect, the one that showed up because HT is endogenous. And the black dots are the direct effect, which is what you'd get if HT was exogenous. And so you see there's a gap between the red and the blue lines indicating a bias. And this is an asymptotic bias. There's no T here. This is really what you'd get if you'd have an infinite number of observations. And same goes, so expansions and recessions have a gap. You say, oh, this is very tiny. Indeed, it seems very tiny, but if you compute it as a percentage of the true population parameter, you get a bias of around minus 10%, and even bigger in recessions. And of course, if you accumulate it, because you're doing these tiny mistakes, but you're accumulating them, you see this gap growing over time. And so now, of course, we can make this gap bigger depending on the choice of the parameters, and that's what these pictures show. So here again, in recessions, we have a much bigger gap than before, and it's due exactly because this indirect effect is much bigger now. And so the bottom line is that we also have, so you see, for instance, if you look at the cumulative sum, we have much bigger gap here. And this is because the parameters of the model have changed and make these indirect effect much bigger. And so that's another DGP, but let me stop here. What we've done in this paper is to come up with a set of sufficient conditions under which the state-dependent LP estimator is consistent for a particular notion of a conditional impulse response function that we define in the paper. And essentially, the main results show that if you run these state-dependent LPs, they will recover that object of interest when we assume the state to be exogenous with respect to the shock. But when that is not the case, you may have a bias, and this by this I mean an asymptotic bias, so the estimate will be inconsistent. And that, how big that bias is will depend essentially on the problems, on the way you generate HT. And I would say that the overall message here is that, people have been running these state-dependent LPs with the idea that they don't require us to take a stand on the model, the whole multivariate model, and they don't require HT, a particular DGP for HT. But at the end of the day, what our results suggest is that, in fact, researchers that use this approach should carefully think about what goes into these HT indicators, because that could impact the validity of their impulse response functions. Thank you.
Thank you very much, Silvia. Very interesting talk.
Sorry, I went over our time. I'm really sorry.
That's perfectly fine, no problem. Thank you very much. I'm going to stop the recording and we can then move to questions and comments.